right, so now we're going to transfer gears and make this a little more complicated with our chi-square independence test. The reason this is called an independence test is what we're wanting to show is, does the second variable that we want to introduce into our matrix differ independently from our first variable? What I mean by that is, let's say in the example that I had laid out last time, like let's say that what we're going to be looking at is, now it's not just that, Sal is saying that Sue's getting more new client referrals. Now we're wanting to propose, maybe there's been a complaint that, anytime a male client comes in, it always goes to Sue. Okay. And so now we're not just wanting to analyze if the distribution of new clients is divided evenly between Sal and Sue in the way that we would expect. Now we're adding another level to it, and we're also looking at the male clients compared to the female clients. Now, if these are functioning independently, what we would expect to happen is that the rates of male and female clients vary independently from whether or not they're assigned to Sal or Sue. Okay? Or, worded another way, because we can do our matrix either way, worded another way, the number of clients assigned to Sal and Sue vary independently from if the clients are male and female. So it's a test of independence. Are these things varying on their own, or is there a link between the way that they're varying? Okay? Now, I've actually gone ahead and worked out some of the calculations here, and then we'll switch to Excel for some of them because I don't want to try to sit here with a calculator and doing this. So I've worked some of this out in advance. But so the situation that we've created here is, let's say that we've gotten, sorry, my kids are home and you might hear screaming in the background. The situation that we have worked out here is we've gotten not only the new clients from Sal and Sue, let's say this is 2 quarters, but we've also gotten the breakdown of male and female clients. And let's say for this example, Sal's working part-time and Sue's working full-time to account for this discrepancy, right? Because if we were doing like the last example, this 165 versus 55 might be something we would want to explore on a chi test on its own. But let's say for this example, this is okay. This breakdown of only 55 new clients to Sal and 165 to Sue, that this is not a problem, all right? So what we found is that in the last 2 quarters, Sal had 25 new male clients, 30 new female clients, for a total of 55 new clients. Sue had 130 new male clients, 35 new female clients, for a total of 165 new clients. Now, one thing with your table, the rows and the columns should both add up the same way, right? So we could say there was 155 total new male clients. Ignore these percentages for now. There were 65 new female clients. So if we add up male and female new clients, we have 220. If we add up Sal's new clients and Sue's new clients, we have 220, right? Our matrix should work out both ways. If you can't add it up both directions against the same number, you've imputed a number wrong somewhere, right? Because either way, we're talking about these same 220 new clients, whether we want to break it up as, was it Sal's client or Sue's client, or if we want to break it up as, is it a male client or a female client? Now, just so you know, this does not have to be a 2 by 2, right? We could look at Sal and Sue and Shauna and Tony, and like we could look at however many salespeople we wanted as part of this. So it does not have to be a 2 by 2. I'm wanting to keep it simple for this example. If it's bigger, that will affect the calculation of degrees of freedom later on, though. So what we're going to do first is the percentages that I've broken down here is what I did was I calculated, sorry, allergy season, of these 220 new clients, 30% of them were female and 70% of them were male. Okay, that was just simple calculation. 155 over 220 is 0.7, 70%. 65 over 220 is 0.3, 30%. Okay. If you had these in PSPP or SPSS, you could obviously do a super quick frequency table and get your percentages if you were working with a more complex table. So we know 70% of the new clients in these 2 quarters were male. 30% of the new clients in this quarter were female. So if these are functioning independently, we would expect Sal and Sue's new male clients to both be about 70% of their new clients. And we would expect Sal and Sue's female clients to both be about 30% of their new clients, right? Because we would expect this to break down fairly evenly. We would expect gender to be functioning independently of what sales rep they were assigned to. So, I'm just making sure I'm going in order on my notes because I don't want to skip around and then do something in a different order. All right, so we have our 70% and our 30%. So we can do some very simple calculations with this, and then I'll show you how to do the more complex calculations in a cheat sheet in Excel, because obviously I don't have the room to write out everything we need to do here. So what we're going to do first is we're going to say, okay, if I expected 70% of Sal's new clients to be male, and Sal had 55 new clients, I can say of those 55 new clients, I would expect 38.5 of them to be male, okay? Because 70% of 55 is 38.5. And I would expect 16.5 of them to be female. Now, it's okay that there's a 0.5. It's okay that there's a half, because we don't have an error here saying, well, you're estimating half of a person. Again, it's just an estimate. It's something for us to compare to mathematically. Now, let's go over down here to Sue. If we would expect 70% of our clients to be male, we're saying that we would expect 70% of her 165 clients to be male. 70% of 165 is 115.5. 30% of 35 is 49.5. So what we're in essence saying here is based on the overall distribution of male clients and female clients of all of our new clients, we can apply that distribution to Sal and Sue for our expectation, for our expected value to compare with our observed value. So in this example, our expected value is the things in the orange, and our observed value, or our actual count, are the ones in the green. So now what we're going to do is we're going to go through for each of these 4 cells, and we're going to do the same chi-square formula that we did last time of observed minus expected, all of that squared, and divided by our expected value. We're going to do this for each of these 4, and we're going to add them up. And that's going to get us our chi-square independence test. Now, before we move on to and I'll actually put all this in Excel and show you a shortcut formula for how to do it. But before we move on to that, real quickly, degrees of freedom for this are going to be calculated a little bit differently. We're not just going to be able to say groups minus 1. So for this, what we're going to do is that, let me find a color I haven't used here. Degrees of freedom is going to equal the number of columns minus 1 multiplied by the number of rows minus 1. Okay? So for this example, we have 2 columns and we have 2 rows. So we'd have 2 minus 1 times 2 minus 1. So we'd have 1 minus 1, or 1 times 1, I mean. So we'd have 1 times 1, so we'd have 1, all right? So see, columns minus 1 times rows times 1, 2 columns minus 1 times 2 rows minus 1, 1 times 1 is 1. So once again, for this example, our degrees of freedom is going to be 1. And that's where I said it would start getting more complicated if you had way more columns and rows, because then obviously this would change this calculation. One more thing before we move into the actual calculations on Excel to be aware of is that we do also have an effect size test that we can use for a chi-square independence test. And that effect size is represented by the Greek letter phi. And phi looks, I'm running out of colors to use. Staples needs to get more colors of their markers. Phi is going to look something, a lowercase phi, is going to look something like this, like a circle with a vertical line through it, okay? That's a phi. Now, and I will show you how to calculate phi whenever we get into our Excel. But phi is going to be our chi-square value that we come up with after adding all these together. Phi is going to be our chi-squared value divided by our total number of cases. So for this example, when we get our chi-square value, we are going to then divide it by 220 because that is our total number of new clients we're looking at, okay? And I can write that down in case anyone's, I need a bigger board. So phi, how can I do this? I'm going to assume that you have copied down Degrees of Freedom and you can find it in your book. You can always rewind me if you did not. All right, so our phi equals our the square root of our chi-squared over our n, okay? So square root chi-squared over n. Now, this is going to follow similar effect size rules that we've been talking about for the rest of the semester. So 0.1 is going to be small, 0.3 is going to be medium, moderate, and then 0.5 and higher is going to be large, okay? So after we calculate our actual chi-square, we can calculate our phi, and we can look at our effect size measurements.